In the last lecture, we discussed introduction and basics to electron beam dosimetry, and compared an electron beam to a photon beam, and then we compared low energy electron beam to a high energy electron beam. We discussed the major particulars about those percent depth dose beams and the characteristics. And I kind of drew out this table, and this is something that you should keep in mind, as well as these are definitely points that should be memorized and kept for your board exam. So after talking about the basics, let's talk about how you calculate monitor units for electron fields. So electron fields are set up as a fixed SSD field. They are not parallel opposed. They are not wedged. You do not use MLCs. The electrons are usually set up as a single field. In rare circumstances, we will create abutting electron fields to treat curved body surfaces, but those are far and few between. The monitor unit equation is similar to photons. Where we have monitor unit is dose and centigrade on top. An output factor is the output factor for the particular cone that you're using. Most linear accelerators come with 5 or 6 cone sizes. The standard cones and a variant are 6 by 6, 10 by 10, 15 by 15, 20 by 20, and 25 by 25 centimeter cones. The next is we have a cutout factor, COF. Output factor has to do with the cone size. Cutout factor has to do with the size of your cutout that you place inside of the cone. Isodose line is your prescription or your normalization. Typically it's 90%, as described by the last video. And then an inverse square law, which I believe the soft chalk lectures describe it as a gap calculation, which is used for extended SSD electron treatments. So going first with the output factor, on linear accelerators, the machines are hard-coded so that when you insert a particular electron cone into the machine, it automatically dials up a set of field sizes. Those field sizes are hard-coded because the output that you get from the electrons varies dramatically on field size. So instead of the therapist being able to dial up whatever field size they want to, the physicist only has to measure one set of output factors per cone because the jaws always go to the same spot. The cutout factor can change. You can have multiple different shaped cutouts, almost an infinite number. Most departments have a standard cutout set that they use that they put in the data book. Some facilities don't have any library, and the physicist will measure the cutout for each patient. The isodose line is typically prescribed at 90%, as described by the last lecture. Historically, they used to prescribe electron prescriptions at 80%. Now 90% is pretty much the standard. Sometimes for higher energy, the physician will tweak it to 95%, although 90% is usually the standard. And the inverse square law again is a gap calculation. We need an inverse square law because as we change from 100 centimeters to 105 or 110 centimeters, the output of the machine changes as we change the distance from the calibration point. Inverse square law is interesting. I'll make a small comment on this. I won't go too much into it. Is that the inverse square law always depends on the distance from your source, your point source. But with electrons, there is no point source because in the treatment head of the machine, typically for photons, I shouldn't say typically, for photons, you have the electron beam comes down out of the bending magnet, hits the target, and then you get the shower of Bremsstrahlung X-rays below. This becomes your source, your point source for the X-rays. For electron treatments, that target is moved out of the way. Target is moved out of the way. Electron beams come out of the bending magnet. There's no target. They come straight until they hit the scattering foil, and then you get a shower of electrons that come down here. So you might say when doing an inverse square law, well, what's my SSD, my source to skin distance? Here there's a source to skin distance. Here's my source. There's no source here. There's no source here. My electron beam comes out of the accelerator through the bending magnet and then down. There's no particular source. So what we do is you kind of back it backwards extrapolate the quote-unquote divergence of this beam, right, backwards to a point in space that you call the source, or the virtual source. So you have a virtual source to skin distance, or an SSD effective source to skin distance. So dealing with it, dealing with the electron dose calcs, typically if you have a patient surface here and then you have a tumor, two centimeters deep, physician's going to prescribe 90 for a 10 by 10 cone. Oh, I should make a comment. Typically, departments they have a standard cone size that equals 1.0 for their output that they do their calibration for, just like photon energies. 10 by 10 is standard. Normally, 10 by 10 is standard for electrons, although it varies by institution. Some institutions do 15 by 15. A lot of times, you won't see very much change between the outputs for a 10 by 10 and a 15 by 15 cone size. In fact, I encourage you to look at your different output factors for the electrons, and you'll notice that there's not a huge difference between them, just a few percent. He's going to prescribe an energy, a cone, maybe a cutout. In this case, we'll just say open. He's going to prescribe it at a specified SSD and depth, usually Dmax. He's going to deliver 200 centigrade. So the physician's going to give you energy, SSD, cone, dose, and then a normalization. Okay. Even though departments have percent depth dose tables with their electron data, normally physicians prescribe at Dmax, and instead of adjusting by percent depth dose, they might tweak by normalization percentage. So instead of prescribing at 90%, they want it to go a little bit deeper. We'll prescribe at 87% or 85%. The exact same thing can be done by adding a percent depth dose factor and calculating to a different depth. They both do the exact same thing. All we're doing is normalizing the dose to a deeper point in space. And by normalizing the dose to a deeper point in space, we are pumping more monitor units in to drive that dose deeper. So for this case, MU is going to be 200 centigrade. My 10 by 10 output factor is 1 centigrade per MU. My cone factor, since it's an or my cutout factor, since it's an open field, is just going to be 1.0. I don't have any additional cutout factor. My isodose line that I'm prescribing to is 90%. And since I'm at 100 centimeter SSD, my inverse square law factor is just 1.0. If we take 200 divided by 0.9, we end up getting 222 MU. This is fairly standard. Some places are fairly particular. If you go to, they want everything written out exactly, and maybe the output factor is 1.01. You know, it's 1% higher. 1.02. It's not going to make a huge difference in this number. 222 for 200 centigrade is a pretty standard number at 90%. Okay. Even if you use a different cutout, and the cutout factor, let's say the cutout factor gives you 1.005. Okay, so my MU is going to be 200 divided by 1 times 1.005 times 0.9 times 1. So if I take 222 divided by 1.005, I get 221. So even though I put a cutout factor in here of 1.005, I still get 221, which is about a 0.5% different from 222. Okay, so this is the standard for monitor unit calculations for electrons. These are what the physician is going to give you. He's going to give you, he or she is going to give you energy. They're going to give you SSD, depth, which normally is going to be Dmax. Okay, they're going to give you dose prescribed at some sort of isodose line. Okay, cone size. These you should be able to do on the fly. Electron calculations are extraordinarily easy, and you should be able to go out to the machine. The physician has an emergency patient that's coming in, a fungating mass, and he calls the dosimetrist out to the machine and says, I need to deliver 500 centigrade in one shot. We're going to do 100 centimeter SSD, 9E to 90% for a 15 by 15 cone size. Okay, you should be able to whip this out without any problem at all. So there's one factor in here that I didn't put, was PDD. Normally the percent depth dose is 1.0. Okay, it's 100% we're prescribing to Dmax. If we're not prescribing to Dmax, then you need a percent depth dose factor that modifies the attenuation of the beam.